Here we are going to discuss the unsteady Bernoulli equation, which is satisfied by ideal flows. And we just discussed that ideal flows satisfy the Euler equation, right? Here I wrote the force, the body force term. I'm assuming that the body force term derives from a potential, so it's a conservative force, such that the force can be written as minus the gradient of a force potential. So this is our body force here. Remember also that we assume the flow to be ideal. That includes irrotationality. And one way of writing that the flow is irrotational is to say that it derives from a velocity potential. Now, the force potential and the velocity potential are different. They're not related. Here we're saying that the force is conservative, and here we're saying that the flow is irrotational. Now, we've discussed inviscid flows before, or we've discussed flows that satisfy the Euler equation before, and we did that on 13th of October. And by playing a little bit around with the u grad u term in this equation, we came to this equation here. So rho partial u partial t plus the gradient of this here, which became the Bernoulli equation, is equal to u times the cross product of omega. What we did to derive the Bernoulli equation is we assumed that we had an unsteady flow, steady flow. So this term came out, and we projected that on the direction of the flow. So we take the dot product with u. Now, if we assume the flow to be irrotational, then this term here is strictly equal to 0, and therefore, if the flow is irrotational, we have that the left-hand side of this equation is equal to 0. What I'm going to do now is write u as the gradient of phi, and therefore what we have is that rho times partial t of the gradient of phi plus the gradient of 1/2 rho u squared plus p plus phi is equal to 0. You see that you can take the gradient out here, and you can write this as the gradient of a big scalar quantity, which is rho partial phi partial t. This term here, this is a scalar, this is a scalar field. This term comes from the unsteady term. So this comes from the rho du dt term, plus the rest. So plus this term here, right? The 1/2 rho u squared comes from the u, previously came from the u grad u term in this equation, plus pressure, which came from the minus grad p term in the momentum equation, plus your force potential. And this here is equal to 0. And of course, what you have is that if the gradient, note that this is a scalar field, and if the gradient of the scalar field is equal to 0 everywhere, and this is true everywhere because omega is equal to 0 everywhere, that means that this quantity, this scalar field, is a constant. So for an ideal flow, the momentum equation reduces to rho partial phi partial t plus 1/2 rho u squared plus the pressure plus the force potential is equal to a constant which is independent on the location. So this is true anywhere. This is called the unsteady Bernoulli equation. And note that when we integrated here, we integrated, this is only a spatial derivative, so this constant might be a function of time, it could be, but it is in any case independent of space. So this is really just a constant. So this unsteady Bernoulli equation looks a lot like the Bernoulli equation, right? So you're used to not having this term, that being a constant, and this, but there are several differences. So let's assume that the flow is steady, which means that this constant does not depend on time, and this term is not here. So then our unsteady Bernoulli equation becomes 1/2 of rho u squared plus p plus phi equals to a constant, which looks like the other statement of Bernoulli, the other Bernoulli equation we discussed before. But the main difference here is that this constant is the same everywhere, which is different from the Bernoulli statement that we derived before. If you cannot assume the flow to be irrotational, if you do not assume the flow to be irrotational, then you have to apply Bernoulli along a streamline. Whereas here, you don't have to apply Bernoulli along a streamline. You impose the Bernoulli equation directly and everywhere. So you can write that this function has to be the same everywhere, and you can identify the constant anywhere you want. You don't have to follow a streamline. So this is a strong statement of Bernoulli, and it does not depend on the streamline. Now note that in general, if you have an ideal flow, if you can assume the flow to be ideal, then the unsteady Bernoulli equation is the statement of momentum balance where you want to start. All right, the last observation which I want to make, is the following. So the way you will oftentimes use the unsteady Bernoulli equation is the following. Here you can see that if we know what the velocity field is, that means that we will know u squared, we will know the velocity potential. So if we know the velocity field, so if we know these terms, then we know the pressure field, right? And so that is actually how you will most of the time use the unsteady Bernoulli equation. We will find what the velocity field is, because we can make a lot of assumption. If we assume the flow to be ideal, we already know a lot about the velocity field. We know that it is incompressible. We know that it is irrotational, so it is easier to compute the velocity field given the boundary conditions, and then we can directly relate that to the pressure field. So when the flow field U is known, the pressure field P, and therefore all of the forces, is known.